Welcome back. This is episode 3 of Everything You Need to Know About JPEG. Last episode, we began work on the JPEG decoder by reading JPEG markers and storing the relevant data into some of our own structs. The next step, chronologically, would be to decode the Huffman data. This would turn the Huffman-coded bitstream into a giant MCU array. But before we do that, let's figure out how to write a giant MCU array to a bitmap file. For the sake of this episode, we're going to pretend that the work involved in episodes 4 through 7 is already done. At the end of episode 7, what we have is a giant MCU array that has been fully processed and now has all correct RGB values. From that point, the last step is just a matter of writing those RGB values to a bitmap file. This episode should be a lot lighter than episode 2, not quite as much heavy material to get through. So hopefully it shouldn't take too long and it should be pretty fun. There's only a few things that makes this a little bit tricky, so let's jump into it. For now, as we try to reason about writing a bitmap file, let's imagine we're using an image that is 24 by 24 pixels. That would be a JPEG that is 3 MCUs by 3 MCUs big. As we'll see in just a little bit, these 9 MCUs will be stored in an array, from left to right, top to bottom. So this will be index 0, index 1, index 2, and so on. As we are writing the pixel values to the bitmap file, we can't simply process this entire first MCU and then the entire next MCU because in the bitmap file, entire rows are stored. So at some point in time, we're going to be writing these top 8 pixels to the bitmap file and then have to write the 8 pixels at the top of the next MCU and then write the top 8 pixels of the next MCU. And then separately from that, write the 8 pixels from the next row of all 3 MCUs. So what this means is we will have to visit every MCU up to a total of 8 times to write each of that MCU's row of pixels to the bitmap file. We can't conveniently write this MCU to the file and then this MCU to the file and then this MCU to the file. So how we write the pixels to the bitmap has to be a little bit more clever. Remember what the index of each MCU is. It would be nice if we could think of this like a nested for loop where we have an X value indicating the selected column and a Y value indicating the selected row. And in our nested for loop, X increases moving across the row, which would cover the first row of pixels. Then X would reset, selecting the first column again, and Y would increase to select the next row. Again, X would iterate across every column again, moving down the row, which would then write the whole second row of pixels to the bitmap file. This is a very traditional use of an X and Y coordinate in a nested for loop to traverse a 2D array, except we don't have a 2D array. We have a 1D array of MCUs, which are themselves 2D arrays. So if we think about it like this, where X goes from 0 to 23, and Y goes from 0 to 23, with these two pieces of information, X and Y, we need to be able to identify the correct pixel. And to do that, we need 3 different pieces of information. We need the index of the MCU, which is between 0 and 8, in this case anyway, and we need the X and Y coordinate inside that MCU. And those coordinates inside the MCU will be between 0 and 7. So what I mean by this is if, for example, X and Y are 0 and 0, we know we're talking about this pixel right here. To be able to read this pixel out of our MCU array and write it to the bitmap file, we need to know the index of the MCU and the X and Y coordinates inside that MCU. In this case, it's pretty obvious that when X and Y are both 0, our MCU index is 0, and our coordinates inside the MCU are 0 and 0. If we call these coordinates 5 and 2, our MCU index is still 0, and our MCU coordinates are 5 and 2. If our X and Y coordinates are 8 and 0, Now you can see our MCU index is 1, and our MCU coordinates are 0 and 0 again, because the pixel we are looking at is in the top left corner of this MCU. If we look at these coordinates where x equals 17 and y equals 4, now our MCU index is 2, and our MCU coordinates are 1 and 4. If the x coordinate is 0 and the y coordinate is 8, our MCU index is 3, and our MCU coordinates are 0 and 0. Just a couple more samples here. If x and y are 12 and 12, our MCU index is 4, and our MCU coordinates are 4 and 4. Lastly, if our x and y coordinates are 23 and 23, our MCU index is 8, and our MCU coordinates are 7 and 7. So as I said before, the x and y coordinates of the pixel will always be between 0 and 23 in this case, because our image is 24 pixels by 24 pixels. The MCU index will always be between 0 and 8, because there are a total of 9 MCUs, and the MCU coordinates will always be between 0 and 7, because MCUs are always 8 columns by 8 rows. The whole point of this is that we want a simple nested for loop that takes x from 0 to the width and y from 0 to the height, but then we want to use the two coordinates to determine the correct MCU to read from and the coordinates inside of that MCU to read from to grab the correct pixel as we are writing whole rows of pixels into the bitmap file. So let's just really look into this table and see if we can figure out a way to calculate these 3 numbers based on these 2 numbers. So what observations can we make from this table? Well, when the pixel coordinates are less than 8, the MCU coordinates are the exact same value. And that makes sense. But what about whenever the pixel coordinates are not less than 8? How do we turn them into valid MCU coordinates that are less than 8? The answer is modulus division. If you don't already know, modulus is notated with the % sign. In order to take any number and turn it into a number between 0 and 7, you want to modulus divide by 8, 1 greater than your maximum valid value. So if we take this 8, for example, 8 mod 8 is 0. Modulus means if you were to perform an ordinary division, what is the remainder? We know 8 divided by 8 is equal to 1, and the remainder is 0. This is directly the answer. So 9 divided by 8 equals 1 with the remainder of 1. That means that 9 mod 8 is equal to 1. Also, if we take a number smaller than 8, such as 6 divided by 8, that equals 0 with a remainder of 6. Then that means that 6 mod 8 equals 6. Any non-negative number mod 8 equals some non-negative number that is less than 8. In our case, we are modding by 8 because we want an answer between 0 and 7. So this shows how we take the pixel coordinate 8 and turn it into the MCU coordinate 0. If we consider this 17, 17 mod 8 is the remainder of 17 divided by 8. 17 divided by 8 is 2 with a remainder of 1, so this answer is 1, which we can see right here. If we look at this 12, 12 mod 8 is the remainder of 12 divided by 8. 12 divided by 8 is 1 with a remainder of 4. That's how we get this 4. Lastly, if we look at 23, 23 mod 8 gives us a remainder of 7. That is how we use the x and y pixel coordinates to calculate the x and y MCU coordinates, but we still have to figure out how to calculate the MCU index. The solution to this is a little bit more subtle. Looking back at our 9 MCUs again, let's number the columns 0, 1, and 2, and number the rows 0, 1, and 2. Now it's kind of like each MCU has its true index between 0 and 8, but each index also has a column number, or an x-coordinate, and a row number, or a y-coordinate. So instead of using the x and y pixel coordinates to directly calculate the MCU index, we can use these x and y pixel coordinates to calculate the x and y MCU coordinates, then use the MCU x and y coordinates to calculate the true index of the MCU. Keeping in mind that in this case, x and y go from 0 to 23, when y is between 0 and 7, we want to map these pixel y coordinates to this MCU y coordinate. When the pixel y coordinate is between 8 and 15, we want to map these pixel coordinates to the MCU coordinate 1, and we want to map y coordinates from 16 to 23 to the MCU y coordinate 2. So what do each of these three ranges of numbers have in common? Well, all of these numbers from 0 to 7, if you divide them by 8, which is the height of an MCU, the result of that number divided by 8 is 0 if you discard the remainder. In other words, if you perform integer division. And numbers in this range from 8 to 15 divided by 8 always equals 1, and every number from 16 to 23 divided by 8 always equals 2. So if we adjust our table, we can calculate our MCU's x-coordinate and our MCU's y-coordinate. These values are the pixel x and y coordinates integer divided by 8. As we already demonstrated, all values from 0 to 7 divided by 8 results in 0. All of the values between 8 and 15 when divided by 8 results in 1. And all the values from 16 to 23 when divided by 8 results in 2. And then the MCU index can be calculated from these new coordinates. That is done using the trick we've talked about before, where you take the y-coordinate, multiply that by the width of a row, and then add the x-coordinate. And the width of a row is referring to the number of MCUs in a row, which is 3. So in this case, with an x and y coordinate of 0 and 0, that is the y-coordinate 0 times the width, which is 3, plus the x-coordinate, which is 0, which gives us the MCU index, which is 0. In this case, where x and y are 1 and 0, y, which is 0, times 3 plus 1, which is x, equals 1. And that is the MCU index in this column. In this case, where x and y are 2 and 0, y, which is 0, times 3 plus x, which is 2, equals 2, which is our MCU index right here. In this case, where x and y are 0 and 1, we have y, which is 1, times 3, plus x, which is 0, equals 3, which is our MCU index here. When x and y are 1 and 1, we have 1 times 3 plus 1, which equals 4. And lastly, when x are 2 and 2, we have 2 times 3 plus 2, which equals 8. Notice that the greatest possible values for these x and y coordinates is 2, because the width and height in terms of MCUs are 3 and 3. The width is 3 and the height is 3, so the greatest x and y coordinates are 2 and 2. And when we use the greatest possible coordinates, 2 and 2, we get 8, which is the greatest possible index. The index of the last MCU is 8. Just to make sure we haven't lost sight of the goal, what we're trying to accomplish is have a nested for loop that loops x and y in terms of pixels from 0 to the width and from 0 to the height, and just using those coordinates, grab the correct MCU from the MCU array, and from that MCU, grab the correct pixel, using the x and y coordinates inside that MCU. One other important detail about writing to a bitmap file, though, is that each row, its size in bytes in the file, must be a multiple of 4. In this example we've been using, the width is 24, but there are 3 color components, R, G, and B, so the number of bytes we write is 24 times 3, which equals 72, which is an even multiple of 4. So we don't have to worry about the fact that in a bitmap file, the size of a row must be some multiple of 4 bytes. But what if our image was not 24 by 24? What if it was 23 by 23 pixels and the last column and the last row were not part of the image? That doesn't affect our ability to write the pixels to the file, because instead of x and y looping from 0 to 23, they'll just loop from 0 to 22, so that's fine. However, now a row is 23 pixels wide times a byte for each color component, which means a row in the file will take 69 bytes, which is not a multiple of 4. What we have to do is, after we're finished placing every row in the file, if this value is not a multiple of 4, we have to pad the row in the file with a couple zeros so that the size of the row is a multiple of 4. So in this case, we need to place 3 zeros. We need to pad each row with 3 bytes to bring the size of a row up to 72. But that 3, the fact that we need to pad with 3 bytes, how do we calculate that? Well, we know if the width is 23, we need 3 padding bytes. If the width is 24, we need 0. And if you did the math, if our row was 25 pixels wide, we would need 1 padding byte. If the width was 26, we need 2 padding bytes. If the width is 27, we need 3. And if the width is 28, we need 0. So the number of padding bytes we need cycles 0, 1, 2, 3, and then starts over again at 0. And these zeros land on when our width of the image is a multiple of 4. So calculating the number of padding bytes is as simple as the width mod 4. One more important idea before we move on. This is something that will come in handy in a little bit. As you know, we read the pixel height and width of the image from the start of frame marker in the JPEG file. We need to know how to calculate the MCU width of the image, how many MCUs fit in a row, as well as the MCU height, how many MCUs tall is the image. In our example where the width and height are 24, we already know that the MCU width and MCU height are 3 and 3. At a glance, it might seem like we just calculate this by dividing the width and height by 8. But what if, again, we consider an image that is 23 by 23? In this case, if we divide 23 and 23 by 8, remember we're always using integer division, so 23 divided by 8 will be 2 point something, which means the result is 2. But we know this isn't correct. Here, even when the width and height are 23 instead of 24, we still need an MCU width of 3 and an MCU height of 3. It's just that we don't use every column and every row of the rightmost and bottommost MCUs. So then you might suggest we need to divide by 8 and then just add 1 to account for that. So then 23 divided by 8 plus 1 is 3, which is the correct answer. But then what if we use this same equation again on 24? 24 divided by 8 is 3, plus 1 equals 4. So by trying to fix the equation for 23, it's now messed up again for 24. Instead of doing something as simple as divide by 8, or as simple as divide by 8 and add 1, we actually need to round up the result of the division. If the height or width is a multiple of 8, when that is divided by 8, it will be some whole integer, so there's nothing to round up. So the MCU width and height will be 3. 24 divided by 8 rounded up is the same as 24 divided by 8 in this case. So 23 divided by 8 is 2 point something, and then we need to round that up to 3. That approach will always give us the correct MCU width and height. But how do we actually do that? You can imagine a lot of ways that involve floating point numbers and floating point division, but we can still pull this off with really simple integer division. If we have our number x that we are dividing by 8, and we want to get the result of this rounded up, we can add 7 before dividing. The reason we use 7 is so that for cases like 23, it changes this division from equaling 2 point something to equaling 3 point something. And then the fractional part is dropped, and the result is 3. But at the same time, when our width and height are 24, by adding 7, we change the result of the division from 3.0 to 3 point something. In other words, when height and width equal 24, 24 plus 7 divided by 8 is the same as just 24 divided by 8. So it's not that this is necessarily complicated, it's just perhaps a bit non-intuitive. The last thing to talk about before we move on to code is the bitmap header. We're just going to be using the simplest options for the header. The header starts with the ASCII codes for BM, so that's the first 2 bytes. That's kind of like how JPEGs start with the start of image marker. Then the size of the file, which we'll talk about in a second how to calculate, and that is 4 bytes. Then 4 unused bytes, so we'll just place 4 zeros. Next is the offset from the start of the file to the start of the pixel array, which based on the header options we're going to be using will always be the address 1A in the file, and that is 4 bytes. And this is the first part of the header, the actual bitmap header, which is 14 bytes. We'll see in a second that the second half of the header is 12 bytes. So to calculate the size, it's 14, the size of this part, plus 12, the size of the second part, plus the size of the pixel array, which is the height times the width times the number of color components, which is 3, plus the number of padding bytes times the number of rows, which is the height, because this will be the total number of padding bytes we insert into the file. So that is how we calculate the size. The second half of the header is called the DIB header. The first thing in the DIB header is its size, which as I already stated is 12, but this is stored as 4 bytes long. Then the width of the image in pixels, which is stored as 2 bytes. And then the height, which is also stored as 2 bytes. The next value is called the number of planes, but it must be 1, and that is stored as 2 bytes. And last is the number of bits per pixel. We've already mentioned that we have 8 bits per color channel, because each color channel's value can be between 0 and 255. It can be any 8-bit number. So the number of bits per pixel is 8 bits for all 3 color components, which means there are 24 bits per pixel. And this is stored as a 2-byte value. And that's it for a bitmap header. It's pretty simple. After this, we store the rows of pixels like we already talked about, with the padding bytes included. So let's move on to coding a bitmap writer. You may have thought it's a little bit odd that we've been talking about MCUs since the very beginning, but we still don't have a struct for them. That's because we haven't needed one until now. So let's add a struct called MCU right next to our header struct. We know an MCU needs a Y, a CB, and a CR component, and we know that the values will be between 0 and 255, but only whenever they are representing the final color data. The MCU struct will be used during periods of time where we are holding on to discrete cosine transform coefficients, which, as we talked about in episode 1, means sometimes these values will be negative and sometimes they will be much bigger than 255. So what that means is in our MCU, the Y, CB, and CR components are going to be signed integers so that they can be positive and negative and small and large. However, we also know that sometimes an MCU will be representing R, G, and B values instead of Y, CB, CR. Just these 3 arrays is enough, but we don't want to be limited so that we have to refer to them as Y, CB, and CR. We want to also be able to call them R, G, and B whenever it makes sense. To do this, we're going to use a union, which in C++ is a way to give the same address in memory multiple names. Unions are also usually used to give the same position multiple types, but we're not going to be using it for that purpose. So here we have a union for Y and R, a union for CB and G, and a union for CR and B. So that is our MCU struct. So now let's look at how we're going to write an array of these MCU structs into a bitmap file. I said earlier that we're going to pretend that the 4 major steps of decoding are already taken care of. That is the Huffman decoding, inverse quantization, inverse discrete cosine transform, and YCB-CR to RGB color conversion. So to avoid having to get into the details, of course, let's pretend we have this function called black box. You give it a header that has the Huffman data vector as well as all the other important information, and it returns a pointer to the start of the MCU array that is created. Then we need to call black box in main after calling read JPEG. So we will call it right here. We get a pointer to the MCU array by calling black box. If something went wrong during decoding, black box will return a null pointer, in which case we can delete the header and continue to the next input file. Otherwise, we need to write this MCU array as a bitmap file. Then delete the MCU array, delete the header, and then move on to the next input file. Before we actually write the file, we need to figure out what the file name is going to be. To do that, let's append .bmp to the end of the input file name, replacing its original extension if there is one. It would be strange, but it's possible that the input file doesn't have an extension at all, in which case just take the input file name and add .bmp. But most of the time, the input file will end in .jpeg, in which case we will remove that old extension and replace it with .bmp. To do that, let's find the index of the last occurrence of a period in the input file name. This will give us the last instance of a period in the file name, and if no period is present in the file name at all, this will return standard string npos. Now we can figure out the actual output file name. I'm using the ternary operator here because I want to conditionally set a constant. Usually to conditionally set a variable, you use an if and an else block, but you can't do that with a constant. But all this is doing is saying if the position of the last period is npos, meaning it is not present in the file name, then we will take the input file name and add .bmp. Otherwise, if the period was found, we take the input file name from the beginning up to but not including the period, and then add .bmp. Then we can write the MCUs to the bitmap. Then we'll add the write bitmap function right here above main. The first thing we have to do is open the output file. Opening the file as output and binary. If the file is not open, then we have an error. Otherwise, let's calculate a couple of the things we talked about earlier. We have the height of the image in terms of MCUs. Which, as we mentioned, is the height in pixels plus 7 divided by 8. The same thing for the MCU width. Then the padding size, which we determined is the width in pixels, mod 4. Then we have the total size of the file, which we know is 14, the size of the first part of the header, plus 12, the size of the second part of the header, plus the size of the pixel array, which is the height, times the width, times the number of color components, which is 3, plus the total number of padding bytes, which is padding size times the number of rows, which is the height. Now that's all the calculations we can do up front. Time to start writing the header to the output file. Start by writing the ASCII codes for B and M. Next, we need to write the file size, but we need to write it as a 4-byte integer. To do that, I'm going to put a little helper function that will help us write 4-byte as well as 2-byte values. It's pretty straightforward to write a 4-byte int to the output file called v, put a byte 4 different times. Bitmaps need 4-byte and 2-byte values written in little endian, which is the opposite of how we have been dealing with 4-byte values in JPEG files. The first byte that we put into the file is the bottom 8 bits. The purpose of binary ANDing the value with FF is to mask away all of the value except for the bottom 8 bits. The second byte we place is the value shifted to the right 8 bits and then ANDed with FF. The third byte is the same except we shift to the right by 16 bits. And then lastly we shift over 24 bits, which will write the most significant byte to the file. And then writing a short, or a 2-byte integer, is the same idea, but we only do this for 2 bytes instead of 4. Now that we have those helper functions, we can write the total file size to the output file as a 4-byte integer. Then write the 4 unused values as 4 zeros. Then write the starting address in the file of the pixel array as a 4-byte integer. That is the first part of the header. The second part, the DIB header, starts with the size of the DIB header, which is 12. Then the width and the height of the image as 2-byte integers. Then the number of planes, which is 1. And then the number of bits per pixel, which is 24. And that is the whole header. Next is to write all of the rows to the output file. I will warn you, at first there are going to be a couple mistakes in this loop because I'm going to write it in the most straightforward, common sense way, which will show us a couple of assumptions that are really easy to make but are actually bad assumptions. But nevertheless, what we need is a nested for loop where y will iterate over every row. Once we have the y coordinate, we can calculate the MCU row, which is y divided by 8, and we can calculate the pixel row, which is y mod 8. Then in this for loop, we need another for loop for x, which will iterate over the columns. Once we have the x coordinate, we can calculate the MCU column and the pixel column, just like we calculate the MCU row and pixel row. And once we have this, we can do the important step, which is calculate the actual MCU index. Which, as we've talked about, is the MCU row times the width of a row plus the MCU column. In other words, the y coordinate times the width of a row plus the x coordinate. We actually have to do the same thing with the pixel. use the pixel row and the pixel column to calculate the pixel index, because the component inside the MCU isn't actually a 2D array of 8 by 8, it's a 1D array of size 64. The difference this time is the width is always 8. Now that we know which MCU in our MCU array we need to look at and which pixel inside that MCU we need to look at, we can write the R, G, and B values to the output file. Now for every row, after we write all the pixels in that row, we have to write the appropriate number of padding bytes. That's as simple as that. Once this entire nested for loop is finished, we have written every row to the output file. All that's left to do is close it. And that's it. Now in main, after we read the JPEG file, we get the MCU array from the black box, and then we write the MCU array to the bitmap file. So let's try running this on cat. And let's take a look. In our folder next to our cat.jpg input file, we have a file called cat.bmp, but something looks a little off. Well, immediately you notice it's upside down, and the colors look really funky. Well, let's look at these problems one at a time. The image in the bitmap is upside down, so that indicates that the rows are inverted in the file. What this outer for loop is doing is first writing the top row of the image into the file, and then writing the row below that, and then writing the row below that until it writes the bottom row of the image to the file. If this results in an upside down image, what if we first wrote the bottom row of the image to the file and then worked our way upward? That would mean starting y at the greatest possible value and then decrementing y until we have written the top row of the image to the file. So instead of starting y at 0, we will start at the height minus 1. And instead of incrementing y, we will decrement y. You might also think we have to change this condition to read while y is greater than or equal to 0, but we are using an unsigned counter. If it's unsigned, it is always greater than or equal to 0. This is one of the beauties of unsigned integers. This condition doesn't have to change. On the last iteration of this loop, y will equal 0. Then when it is decremented, because it is unsigned, will become the largest possible integer, which is not less than height, so the loop will end. And that is exactly what we want. So let's try running this again. So that fixed the problem of the image being upside down, but what's wrong with the color? Well, since the bitmap format has already showed us that it likes to do things backwards, what if we just tried writing the color components backwards as well? Instead of writing RGB, let's try writing BGR. And there we go. Now we can take giant MCU arrays of RGB values and correctly output those pixel values into bitmap files. Now the next 4 episodes are going to be about replacing that black box. But what's nice about being able to write to bitmap files is that we will be replacing the black box in small steps. But each time, at the end of each step, we can output the current state of our MCU array to the bitmap file. Even though it will not be finished, it won't be the correct RGB values, we can output that array of MCUs to a bitmap file anyway and make sure that whatever the current state of our MCU array is, it seems reasonable. So there you go. Hopefully this episode wasn't too bad. Hopefully you thought it was pretty fun. I think this is a pretty entertaining step. Please like and subscribe if you're enjoying this series. I really greatly appreciate it. Stay tuned for the next episode where we begin replacing the black box by decoding the Huffman data. Thanks again, and I'll see you next time in episode 4.